So today we're going to move into some ring theory. Maybe a little more pleasant than groups. I don't know. They have much more structure, so you have more to work with, and it's more familiar, I would say, than groups. Groups takes a lot of getting used to because you have so little you can do. So let's start with definition of what a ring is. So ring R, F, operations plus and times, binary operations, satisfying the following. R plus is a group, new group. Identity is written. Identity, right? Go with identity. Subscript R, but I'll just say 0. Additive identity. Negative of A is the additive inverse of A. Now, unlike a field, this multiplication does not form a group. It's not required to form a group under the, well, even when you take out 0. So, however, you want this to be something called semigroup. It's that's I'll say multiplication associative. And Artin requires, most textbooks will require this, but it's not always required that we have a multiplicative identity. As you write as 1. So there are certainly rings without identity, and those without multiplicative identity. And the third thing is we want something that ties these two structures together, familiar from fields, and that is that we have the distributive property, left and right. See? Now, you'll notice what's not in this list. Makes it slightly different than a field. This is it. That's the end of the definition. Note, not require things that we wanted in fields. One is that we don't require that multiplicative inverses exist, even for non-zero elements. And we don't require commutativity of the multiplicative operation. Now, Now, that said, there's a very vast area of mathematics called commutative ring theory, which is really wonderful and interesting and fascinating. But so there's still plenty of interesting things to study when you do require commutative. But if you put in inverses, then you get into field theory. You put in that in, and that's also interesting, but not at the same level of complexity. Let's write down some examples. So, I mean, one thing you should think about is rings are, as I said, groups are kind of complicated because they have such little structure. Rings are very familiar. Rings are things you deal with all the time. So you always have some kind of system where you have arithmetic. You multiply things, you can add them, and so on. So here are some examples. Okay, so the first thing is fields. We've seen R, handling real numbers, handling complex. We have the finite fields. Have rational numbers of fields. And these make up a lot of the, I think, the main examples that we would look at right now. But there are many, many more. But we can then, when we start talking about rings, so as I said, fields is a very, very, very nice situation. You have all of the things you would want. So, but you can strip out a couple of those things and say, talk about sort of arithmetic kind of things, or arithmetic, like the integers. I take out the need for multiplicative inverses, and talk about the integers, and just work with those. Not, I mean, one thing that would not belong in this list, of course, is the natural numbers. That under addition, we don't have a group. We don't have additive inverses. We need at least additive inverses. But you can sort of extend these a little bit. You could say, okay, well, let's take all things that have a multiple of I, like let's from A plus BI, like a complex number, but now only the A and B can only be integers. Study that kind of a situation. You don't have to do it with I. You could do it with something like the square root of 2. Whatever you want, some kind of real number. So these are rings that are much studied in number theory. People try to understand the basics of numbers by studying these types of things. If you're more into analysis, an analytic setting, of course, you can consider continuous functions or differentiable functions. And say, well, you can do it on all kinds of spaces, but let's just say on R. This would be denoted CR, C naught of R. We talk about differentiable functions. One of R. Or smooth functions, which are functions that have derivatives to arbitrary order. All form rings. C infinity R. Of course, there's some algebraic properties of these rings that oftentimes can neatly summarize some of the properties you're looking for. And of course, in calculus, you know, we don't say the word ring, but we study these like obsessively. We study these rings obsessively. We look at things called, you know, differentials, derivations of these, which are like differential equations and so on. And you can actually put much of that, not all of it, into the algebraic context and have a lot of the interesting things to do. Now, these are all, well, there's, I should say, one other example, which we'll spend some time on today, is the ring of polynomials. And so the ring of polynomials, as I'll describe in some detail in a moment, you can take coefficients to be in any other ring you want. So you can talk about R of X, which are just polynomials with coefficients in your ring R. But if you don't like that, you could think of the reals R of X. Examples would be R of X or integer coefficients polynomials. These are certainly things you'll study. Just look at calculus and all that stuff. Study polynomials, and I'll try to explain what the motivation is for studying these types of things. Which there's actually quite a lot of motivation. What's another thing? Okay, so another thing we would consider, which we've seen maybe one example of above here, finite rings. But the example we have above are fields, and a main example we've already looked at is C mod n. So now you don't have to have n to be prime. You can just have n to be anything and you'll get a ring. Because as we've seen, we can multiply, we can add things mod n and everything, all of our basic properties. Now, all of these examples that I've listed so far are all commutative. They're commutative rings. The multiplication is commutative, and there is sufficiently large body of work dedicated to non-commutative rings. But the most common example of a non-commutative ring would be like a matrix ring, the rings of n by n matrices. With entries that are in some ring R. And you can have R be non-commutative, but then you have to be it's less fun to have R non-commutative. It's not, but best thing is for here R to be commutative. And another example we had of a non-commutative setting that we talked just briefly about would be quaternions. Division algebra. Close to a field, but also non-commutative. Okay. So a lot of different arithmetic frameworks, a lot of different situations you can be in, where you may want to have some general holes over what you can say. And that's what we're doing here is, abstract algebra. Title is really, we want to kind of get as far as we can with a basic structure. And then when we look at examples, really apply some general theorems to those examples. Sort of our perspective. Questions? So I think there's there are a lot of theorems. More in section 4.3, not 4.11. I don't have any idea. Yeah, it's chapter 11. Okay, 11. This is chapter 11. I should have said that. We skipped several chapters, but first two sections of 11 are sort of lean on the theorems, but they're sort of warm-up theorems in there. So here's one warm-up theorem that I didn't write down the number of, but it says, okay, well, let's say we have a ring and the additive identity is equal to the multiplicative identity. Then in this case, R is just 0. Consists of one element, 0. You call the trivial ring. This is an interesting ring in that sometimes you actually don't even want to admit that it exists. You want to just say, no, we don't consider that as a ring. Certainly some texts will say no, that's not allowed. Start that we want. So this is as I said, a warm up. Here's a ridiculous proof of this statement. Okay, so let's suppose A is an element of our ring that satisfies this condition. Well, A is equal to 1 times A. I wrote A times. But now that's equal to A times 0. And now your instinct is to say that's 0, but okay, we don't know that yet. Just have the properties. Nothing with numbers here. But we know that 0 is an additive identity. So 0 is 0 plus 0. And we know we have the distributive property. And we know that 0 is equal to 1. We know 1 is a multiplicative identity. Now we can subtract A from both sides because additive inverses exist. Okay. I'm silly. Comic book or something. If there's like a notion of like a lighthearted theorem, I think like these kinds of things are like lighthearted theorem. Like there's not, you shouldn't feel like, it's just kind of whatever. They're not serious. Okay. So another thing Artin does in this first section of this chapter on rings is he gives a little more vocabulary, and we want to talk. I'm going to build up some more vocabulary. I just want to mention these up. I know that a lot of the stuff is foreign, and so I don't expect people to remember it, every single word that I give as vocabulary, but I would like if people have forgotten it to like just ask. Because I'm going to use a lot of these words, and sometimes I'm not even going to define them because I forget. So just ask me if I'm saying something that doesn't make sense, that you don't recognize. So unit, that's what we're defining in a ring R, is an invertible. It's an element with a multiplicative inverse. So what are some examples? Well, if R is a field, then all non-zero elements are units. So let's look at something that's not a field. I'll give a couple of examples and people can tell me. What about integers? What are the units of the integers?
Just 1 and -1.
Yeah, plus or minus 1. Good. Someone else for polynomials with coefficients and reals. So these are the ordinary polynomials you deal with in calculus. segue into talking about polynomials. So if I have a polynomial, like, do I have an inverse for x plus 1? I multiply that by, okay, these are polynomials. So again, this is, I think, what I was saying before with like groups a long time ago. It's like you really want to think of like narrowing your scope when you're talking about whatever you're talking about. If you're talking about a given group, you want to think, what is in my group? What's possible within my group? Here, same thing with range. When I'm talking about integers, the reason we have plus or minus 1 as our units, because we don't have 1/2, right? We don't have 1/3 or things like that. It's just the integers. Here we're talking about polynomials, not rational functions. Right? A rational function is something like p of x over q of x. Those are what you call a rational function. These are just polynomials, meaning that they look like a number plus a number times x plus a number times x squared plus a number so on. Those are the things that are in this ring. If I want something, I need to find another polynomial that I can multiply this by and get. One. I do that as a function. Polynomial. I do it. But yes. Here. Who says no? I say no. Right? Because if I have, so I can write this polynomial in such a way that this leading coefficient is non-zero. Okay, if it's 0, then I go down until it's not 0, right? And then my leading term here is going to be x to the n plus 1. And so n plus 1, so I'm never going to get no leading coefficient. So this is not invertible. And in fact, the only invertible polynomials here are going to be constant polynomials that are non-zero. F of x, a. There I can multiply by 1 over a. A is a number. This is where, so this is a good moment to kind of move into 11.2, which is really about polynomials. I'll try to explain why these are such important rings. Consider a couple of big reasons. Here R, I'm going to assume, well, again, R can just be any ring, but generally, usually we're going to consider community. What are the elements of this? So an element here is going to be a formal expression that I kind of wrote up above. So I think Arden starts with a constant term and goes to the nth term, but I don't know. I might reverse. Just some formal expression like this. X is a formal variable. And I think it's important to note, like, these are, you can talk about this as a function, but when I write R of X, I generally am not thinking of this as a bunch of functions. I'm thinking of it as formal expressions like this. So here, A naught, A1, these guys are all in a ring. Now, I can multiply these guys as I would ordinary polynomials, right? And I can add them as I would ordinary polynomials. So add coefficients and then use distributive property essentially to multiply. If I have like, is it okay, or should I mean, there's a formula here, but I don't know if it's useful or not. People understand how to multiply polynomials, or people feel okay? Who would like to see me do it? If I have something like this, now if I have F composed or F not composed, I don't want to compose. I want to multiply. It's going to be a sum of C's. So I'm going to write it this way: sum M. Yes. Okay. And then here you have this formula for CK. CK is equal to the sum of equals J. Okay. Of of course, I is going to be N. If you want it. I don't find that to be particularly illuminating. It's just, you can write down these formulas. But it's really what you would expect. You just distribute, multiply, and then add up like terms. You want things with X to the K, they all, you keep them. People want to see an example, or is it okay? Funny because Artin does spend a lot of time on this, on the basic arithmetic of it, and then he skips proving some life and nature here. He's just like, oh, okay, now don't worry about it. Okay, so then now we have a lot of vocab. So we have call these polynomials. What's a monomial? Poly means many. The monomials are things that look like X to the I or something. Your I is an element of the natural. Come on. So polynomials, many of these added. But add a coefficient here, and I think it's kind of safe to still call it a monomial. But I think sometimes people will distinguish that by calling those terms. Degree of a polynomial. That's what you think. So it's just the highest order. It's the highest x, the largest exponent where you have a non-zero coefficient. We have f of x. Say k, where a sub k is a maximum. For a sub k is non-zero. A sub k being the coefficient. So degree is a very helpful thing to have when you work with polynomials, because there's some basic properties of degree. Just write these down. One is that if I take the product, then the degree of the product is the sum of the degrees. That's easy to see. Just maybe look at the formula for case here. The leading order term of the product will just have one I and one j, the both be non-zero. So and another property is that I think that's sufficient for now. Let's continue with doing a little more vocab. Okay, so they're constant polynomials. What are those? Those are just polynomials that don't have any, that have degree 0. Sure. No x. And the last one is maybe a little less familiar to some of you, maybe. It's called monic polynomials. And these are polynomials whose leading order coefficient is 1. The coefficients are, of course, case of i's. Yeah. So yeah, so if we thought of r of x, then like pi or 2 or negative 10, these are constant. They're just degree 0 guys. And whereas, x minus pi is not constant. So we think of them, I mean, there's a perspective here, of course, to think of it as a function, right? Think of it as which I'm trying to dissuade you to do that, but we will want to do that. So it's kind of, you want to take these as formal things at first. We'll also talk about them and how they can be viewed as functions, but they're sort of two different perspectives and you want to bounce them off. If you think of them as functions, a constant polynomial should be a constant function. The converse is not entirely true, or it's not entirely. Well, let me give you an example. If your question spawned that. So why not think of them as functions? You might, just like me, we're asking you to not think of them as functions, or just period. But here's why. So, let me just say not identified. All right. Let's take F2. Let's take 2 elements. One will be x squared plus x. One will be 0. So I can think of a polynomial as a function. That's something you can do. But if I think of this as a function on the only thing you could imagine, at least at first, thinking of it as a function on, is on the coefficients, on the ring of coefficients. In other words, I can put in an element of my ring into that function, into that polynomial, and get a value. So obviously, if my function is 0, my polynomial is 0, then I get 0 constant. On the other hand, I have 2 values for F2. I have 0 and 1. And if I put them into x squared plus x, I'll get 0 squared plus 0 here, which equals 0. I'll get 1 squared plus 1 here, which equals 0, mod 2. F2 is our integers mod 2. So this function, or this polynomial viewed as a function on F2 is exactly the same as 0. Not distinguishable as functions. So, but that's no good because I should think of that polynomial as it's a different looking polynomial. And so I don't want to identify them as the same thing. That's why I encourage you not to think of them as functions, but realize that we can interpret them as functions. Make sense? Okay, Now we want to do, or I want to assert a very important proposition. You all have some experience with, I think. 11.2.9. Vision algorithm. But maybe the super nice one, or like fancy one. With polynomials with coefficients in a ring. So let R be a ring. Now here we do need to make some assumptions because we don't have everything we would want. So we want F to be a monic polynomial. That's a polynomial. Monic polynomial. That means leading order coefficient is 1. And G, any polynomial. Any element. Then there are uniquely determined Q and R. That's that, satisfying at a single equation. F of, oops, G of X. F of X times Q of X plus R of X. And G R of X is less than that of, pretty less than that of F of X. Now, I should say there's one weird exception to the degree function, which is, what if the function is 0? I mean, what if the polynomial is identically 0? The degree is defined to be the smallest non-zero, the degree of that monomial with the smallest non-zero coefficient. So if all of those are 0, then that's kind of a not well defined. So because you don't have a the smallest of an empty set. So in that case, usually people just define the degree of 0 to be negative infinity. That make life easier. But I'm going to use that kind of perspective. But otherwise, this theorem might have some issues. This equation, does it look familiar to people? Does this look familiar?
It's kind of like integration. Let's see if you do like a bunch of integrations in a row.
Like that, maybe. Okay. Yeah, okay, integration, maybe there's something similar with me. I was, what about like, what about the notation here? Q and R. Yeah, R is remainder, Q quotient. Yeah, I think so. Right, you can, it's saying, look, what is this theorem asking about? It's saying I've got a polynomial F, I've got a special one, a monic polynomial, or polynomial G, I've got a special monic polynomial F. I want to divide G by F. I want to do that. I can't do it, but I want to do it, right? And so the best I can do is I can start to try to divide G by F. And I'll get so far, but then I'll have a remainder. And that remainder, by dividing by F, will have a smaller degree than F did. This is very similar to like dividing by numbers. I want to divide, 20 by 7. And I want to do it. I can't do it because 20 is not divisible by 7. But I can say, well, 7 times 2 gets me close, and then I have a remainder that's smaller than 7, right? 6. I think I did that right? It's the same idea here, except now instead of the inequality relating to the size of the number, you've got the degree of the polynomial. That's what you're getting small. Okay, I'm going to do it. I'm going to just say Arten's right. This is just silly to prove it. He doesn't prove it. He just says, hey, you guys know this. I wrote a proof, but I'm like, why would I do that? So the proof is not hard. I mean, you can do a proof by induction. The point is, because of the monic, you really do need the monic condition. I mean, if you don't have it, it's not true. But the point is if you have if you have some degree here, you've got some leading order term like a to the n times x to the n. But f is monic, so f looks like x to the n. So you can multiply by a to the n times, you can bring that up by the power of x and then subtract it from g. And that will lower the degree of everything down by 1. And you keep on doing that until you get to the degree of f, and then you can't, do it anymore. You've got to remain. Now, I want to say you guys have all done this before, but I can't be so sure. Never sure of anything. So, you guys did partial fractions, so yeah. Calculus. I hate to remind people of calculus too. Like the worst experience of life. Maybe not. I don't know. Maybe this course. But like, it's really a painful course. I mean, I hate teaching it, and I don't do it very much. A lot of techniques, but anyway, when you do partial fractions, right? You have like a rational function you're trying to integrate. And the point is you can, you need to kind of divide. You need to make it into a proper fraction. And so you do this division of something like p over q, and you first simplify that into some other polynomial of x plus to the. And this is the remainder. This is the remainder. So it has degree less than the degree of q. And then you can furthermore simplify it by looking at factors of q. So this process, though, is a process that you actually, I'm sure you perform this algorithm at some time. The point is you can do it. You can really do it like you do long division. Right? You guys remember that? So it's very much the same. So I'll stick with Arten. There is a nice corollary. Which does come up, and certainly in let's let g of x be a polynomial. And alpha is an element of R, pardon. Just an element. Then the remainder is R that we have up here. Obtained by dividing of x by the polynomial x minus alpha. Well, it has to have degree less than x minus alpha. And degree of x minus alpha is 1. So it has to have degree less than 1, which means it has to have degree 0 or it is 0. And in that case, it's a constant. And so what is this constant? Well, it's actually just g evaluated. To prove this. So it's a corollary. That's a hint. A corollary means that you are going to apply with the theorem that you just had. We have a theorem, division algorithm. We want to apply it, and we're actually dividing. Let's just state that by an algorithm. Have g of x is equal to our f of x. In this case, we're dividing by x minus alpha. So it's x minus alpha times our q of x plus r of x. But r of x has to have degree, as I said a moment ago, it has to have degree less than x minus alpha, the degree of x minus alpha, which means it has to have degree 0, or it has to be 0. So I can, instead of writing r of x, I'll just write r. There's no real x in this. It's just some element r of r. Okay, what do you guys think? As I said, you don't want to identify polynomials with functions, because different polynomials will give you different functions. However, you can evaluate polynomials at elements of your ring. In other words, I can take x equal to alpha, put it in. If I do that, get this. Alpha minus alpha is 0. Okay, I've got a couple of minutes, and let me, in the last few minutes, explain what's the obsession here with polynomials. I wrote down a list of a bunch of rings that people would be interested in. Why are we talking about polynomials so much? So, one application. So there's a couple of main reasons why. One we're really probably not going to get to at all, but maybe in a future course of more abstract math, you'll learn it. One is to get what are known as canonical forms. So one is obtain canonical forms of linear transformations. There are Jordan canonical form, rational canonical form. These come from studying rings of polynomials. Those forms tell us how we can understand and classify linear transformations, which are all over the place and application. So even just understanding the statement of those theorems is really a great thing. But something that's more, I think, down to earth, and something you may be able to appreciate, is the study of fields. So we can use polynomials the coefficients in the field F to expand F by introducing solutions. Polynomial equations, like f of x. For example, let's say we were in Q, in rationals. Well, rationals are great, but they're sort of limited. I want all of a sudden to be able to talk about a triangle, an equilateral triangle with side length 1. So I need the square root of 2. But then I need to kind of expand Q by adding square root of 2. This is still a field now. It's a new field. It's bigger. And what did I do? I just introduced the solution to this equation, x squared minus square root, or x squared minus 2, which is an equation in Q of X. More familiar example is we can take the reals and we want to go to the complexes. That we need to introduce a solution to a polynomial equation. X squared plus 1 equals 0. We introduce that, we get our I, our imaginary. And that allows us to extend our field to complex numbers. This game is played throughout field theory, and it allows you to, there's this really beautiful connection in these expansions through polynomials and group theory, and groups that will sort of fix polynomials. So, really beautiful subject, but one of the reasons we're studying. All right, guys, I'll see you all Wednesday.
Do you have any time today other than right after this class for like an office hour or something like that?